So now we're finally getting into the mechanical property of the bone. In the previous videos, I have explained the anatomy and physiology of the bone, how they help us in the biological sense. But now, from now on, we'll mostly focus on the pure mechanical properties of the bone. And I'm going to begin this with a quote from Wolff. And he created a law called Wolff's Law of Functional Adaptation. And it states that the shape of the bone is determined only by the static stressing. In other words, that means the bones of the, let's say, the fingers are going to be determined based only on how they are to transmit loads from their surrounding. Okay. Bones have this anisotropy effect, this anisotropy property. And the reason that's the case is because, as I said previously, bones are composite materials. And composite materials are materials that are combined of multiple compounds. In this case, we have the ceramic part, which would be the calcium phosphate, calcium hydroxide in the bone. And there will also be the collagen fibers, which are a different property, which allow for the strength of it. So because they're the anisotropy, that means that the strain and stress curve are different depending on the angle that we pick to test them. So if we were to begin the longitudinal direction, so if we apply force here and apply force here, then this is the curve we would be seeing. As you can see, this means that this can stand a lot more compression or tension, a lot more than it would be if you use the transverse side. Now, geometry does have to play a role, but the real factor is that the collagen fibers are running this way. So it's like having columns or like pillars. And so if you apply a compressive or tensive load, these collagen fibers primarily will be able to withstand it. Whereas if you apply force this way, it'll be a lot easier to fracture. As you can see, this longitudinal curve over here, the elastic portion, is much more steeper than, say, the transverse side, which means that this is a lot more harder or stronger per se. If we move on now to looking over here, longitudinal and transverse, but now we're going to determine the difference between compression and tension. So, as I said, the bone is a composite material, and a composite material has different responses to tension and compression. For a bone, it can have a lot more compression as we see here. The compression can go a lot less than it would be for tension. But still then we can see the transverse property of it, the transverse effect, having an anisotropy effect over here allows for much greater force to be withstand in the parallel direction of the bone. And for this example, I'm trying to use the femur or like a long bone. It will differ when you use the other forms of bone, but to keep it simple, we're trying to keep it as a long bone over here. Okay, strain rate dependency. What that really means is that depending on how fast you pull the bone, the applied stress would differ. So this graph over here is a lot exaggerated. I didn't put an axis over here because I didn't have the exact values, but regardless, we can see that if we are going to strain this bone at a very fast speed, in other words, 1,000 times a second, then what's going to happen is that this bone will be able to withstand a lot more force initially. So if you take the bone and just like apply an impact pressure, just a shock on it, it'll be able to withstand it. But if your rate is 0.01 a second, in other words, if you are going to pull a bone with very slow speed. So you're going to force it but at a very slow speed. Then what's going to happen is that you can see that it will naturally give in. And this effect is known as the viscoelastic effect. And we'll see later how that has effects, especially on tendons and ligaments. A very important effect. And lastly, when we look at bones, we're gonna look at the defects. So as you can see, a normal bone, let's say, should have a maximum stress as over here, and it should withstand all other stresses that happen below here. But if you look at this bone over here, if there is some kind of defect, maybe a natural defect, and at that point, the collagen fibers, as you can see, are going around. In other words, it's not really 100% parallel to the axis. So if a load is applied over here, a compressive load, the load will be transmitted layer by layer until it reaches this point. But because this is not perfectly parallel, this stress concentration will be a lot more higher. In a sense, at this point, it's as if you're like applying a transverse load, in a sense. So we can see here, when you have the defect, the stress at this concentration will be a lot higher. And so this bone would then fracture at a very low stress, even though you would assume the bone to have, realistically, a stress up to here, in the ideal scenario. Yeah, so in the next video, I'll try to explain more of a stress-strain relationship of bone.